Hello and welcome to this MedChemNet interview. I'm Gerald Clarke, Community Manager for MedChemNet. Today I'm joined by Adam Kirrander, Chancellor's Fellow and Lecturer at the University of Edinburgh School of Chemistry. Adam, it's a pleasure to have you here.
Hi, it's great to be here too.
So Adam, could you tell us how you became involved in the research on the use of light in chemistry?
Absolutely. So I'm a computational and theoretical chemist, and as such we calculate the properties of molecules, and really at some point one has to stop and check whether what we calculate has any bearing on reality. And the data that we compare to is generally measured in some way by light, by spectroscopy in some form, spectroscopic measurements and so forth. And so in that sense, light is instrumental to my work. Also, already as a student, I had sort of two lines of interest. So I was interested in structural biology, and so that, of course, there are two dominant techniques, NMR and X-ray diffraction, protein crystallography, and NMR measurements. And in fact, both of these rely on light, because of course we think of light as maybe visible light, but in fact, X-rays, as used in protein crystallography, are also a form of light, and equally the type of frequencies of electromagnetic radiation one uses in NMR can be seen as a form of light. It's still different forms of electromagnetic radiation. So this was the one angle of my interest as a student. And then the second angle was new, very fast lasers that produce light in very short, very brief bursts. And these are sufficiently short to actually be able to look at chemical reactions as they happen in real time, so to speak. And so all my interests in some way in chemistry really were related to light, always, I want to say.
Wonderful. And can you give us some details on what you're currently working on?
Absolutely. So currently I'm very excited because I'm combining, I mentioned this background in protein crystallography and X-ray structural determination of molecules, and at the same time there's interest in kind of making movies of chemical reactions using very short laser pulses. And so over the past 10 years, there's been a very rapid technical development, which has now culminated in a completely new type of machine. So those of you who work with maybe protein crystallography will know synchrotrons, which are machines that produce X-ray radiation, and people determine protein structure using these machines. These are huge facilities. Now, over the past 10 years, people have been building an X-ray laser. And the first machine is now operational. It's called LCLS, and it's an X-ray free electron laser that's built in California, outside Stanford. And there's another one, a facility under construction in Europe, outside Hamburg. These are massive projects, but they actually will combine the sort of molecular movies from the femtochemistry field with the structural determination that people have been doing for ages now at synchrotrons, for instance, as they do in protein crystallography. But it adds the time feature. So we literally see what the atoms do, where the atoms and molecules occur at different times during a chemical process. So we can sort of almost film, if you wish, the chemical reaction. We have molecular structure as a function of time.
What an incredible age we live in, that we can film chemical reactions.
I can't believe my luck. It's so cool, yeah.
So what are the potential applications then of this work?
So in terms of my own interests, which are towards simply making these techniques to work, and then really applications in photochemistry, which is the field where one looks at the interaction of light and molecules. And so in broadly speaking, in my field, apart from trying to develop these techniques and establish the fundamental principles of photochemistry, the applications are very much in things like photonics, where people try to use molecules to, for instance, alter light or store information using light in molecules. Excuse me. And as well, it might be, for instance, photovoltaic cells. So these could very much be improved upon if we had a greater understanding of how molecules actually absorb energy from sunlight, for instance. And so these are examples of areas where we might actually be able to improve things quite rapidly. And of course, in biochemistry, people use, for instance, the green fluorescent protein as a biomarker, and all of these tuning these kind of systems will again mean that we have to understand much better how light affects molecular systems.
Mm. So how is femtochemistry changing chemistry as a field?
It's quite interesting. So femtochemistry as a field has been around for some, roughly speaking, 2 decades. It was awarded a Nobel Prize to Ahmed Zewail in 1998, which maybe can be kind of seen as the official acknowledgement of this field of chemistry as a field on its own. What I think what it's done is there's an ongoing process that is still happening of us being able to study chemical reactions as they happen, and with all the potential implications for developing better materials and better molecules, but also simply understanding better how chemical reactions actually happen. The other side of the coin, which is maybe a bit surprising, is that femtochemistry as a field has also made us more aware of how we can use light to control chemical processes. So it's not just about passively studying chemical reactions in their kind of native form, but in fact we can also use light to modify the outcome of a chemical reaction, or change the rate at which it happens. So some people tend to call light is a new catalyst almost for chemical reactions, and this is something we're exploring more and more.
Wonderful. And is there any kind of medicinal chemistry aspect to your work?
Yes, so I mentioned these new X-ray free electron lasers that allow us to literally film reactions as they happen. So in terms of this type of work, these new X-ray free electron lasers, because they are so very powerful, they're actually able to record the structure of a protein without having to crystallize the protein, which I'm sure many of your members will know is a huge bottleneck in terms of determining the structure of proteins, especially for very popular or very important, rather, drug targets such as membrane proteins. These are horribly difficult to crystallize. And so if one can actually get away from the whole crystallization process and simply have a liquid jet that places the proteins in front of the beam, and then one can essentially determine the structure from many repeated exposures of the same single protein. This could be extremely important, and I think is quite honestly is probably one of the main factors behind the construction of these facilities, because they're of course huge investments, and that kind of biomedical application tends to carry favor with funding agencies. And so absolutely, there's definitely a medchem angle to the whole thing.
And what work are you excited about in this field at the moment?
Well, so at the moment, I think that the entire field is in a very exciting phase. So we recently, myself with collaborators in the US at Brown University and Stanford, recorded the first X-ray movie of a chemical process. At the same time, people working in Hamburg, for instance, the group around Henry Chapman, have been determining the protein structure of not quite yet single proteins, but from nanocrystals that would never diffract in any kind of traditional setting. So I think this entire field is moving forward at an incredible pace, and I think we'll see tremendous changes both in what we can do, so in the technology, and also what these new experiments will allow us to learn about about how chemical reactions happen and about the structure of matter.
So you touched on it there a little bit, but what changes do you think we're going to see in this field over perhaps, say, the next 5 years or so?
So I think there will be a very transformative change in terms of how protein crystallography and I think it will affect structural biology in terms of what we can what targets one can seriously consider. In terms of my own work, I think these new types of experiments will really challenge our ability to model chemical reactions accurately and model the interaction of light and matter, which will push, I think, our computational and modeling abilities necessarily, which will, I think, ultimately, it will lead to us being able to essentially design molecules with interesting photonic properties in the computer. So the way that engineers today construct bridges or houses, buildings in a computer first, I think eventually we'll get to a point where we can do similar things with molecules. So I think this is tremendously exciting. It might not quite be 5-year horizon, but we'll get there, I'm sure.
Wonderful. Well, thank you very much, Dr. Kirrander. It's been a pleasure having you here.
Absolutely, it's been fun. Thank you so much.